Hello everyone, this is Spencer from Hydromantis. Well, it's about 2 o'clock here, so I think we'll get started with today's webinar, which is about modeling air emissions from the petrochemical industry using our Toxchem package. And it's about a 30-minute webinar today, and so I'm going to get started, and we may have a few other people join us as we move along here. I just want to have a couple of words at the beginning here. I just found out a little earlier this afternoon that they're testing the fire alarms here in the building that I'm sitting in, and so if you suddenly hear sirens and bells ringing and so forth, I'm just going to keep plowing through as we move along here. So this is GoToWebinar service here that I'm using, and there is available to you a chat window and a questions window. So if at any point you have any questions as we go along, please feel free to type them in, or you can also use your raise the hand function there, and if I see that you raise your hand, I can activate your audio. I'm going to leave everybody on mute for the moment, however, just so that as I've experienced in the past, it tends to get a bit noisy. So, but anyway, grab my attention if you can, if you have any questions. And I'm going to leave some time at the end of the webinar here to do some questions and answers. Okay, so to get rolling here, I'm going to get my slides started. And for those whom I've not met before, my name is Spencer Snowling. I've been here at Hydromantis for about 12 years. I've led for most of that time the research and development of many of our products, specifically spent quite a lot of time developing GPSX, our activated sludge process modeling software, and more recently I've been helping with the development of Toxchem that we'll be talking about today. I'd also like to give a quick acknowledgement to Dave Kajowski from Refinery Wastewater Engineering and Associates. Dave and I have been working together now and again for the refining and consulting services to a number of refineries in North America. And Dave helped me put together a couple of the examples that are here today, and he's on the call, and I'm going to be bringing him in a little bit later on. So the plan for today is just to do a brief introduction to Hydromantis, just if you've never had the opportunity to hear about us before, to talk a little bit about modeling refinery wastewater treatment itself, and then I'm going to do an introduction to Toxchem that we'll be demonstrating today, and that will include doing a live desktop demonstration where I will be building a plant and adding some components to the waste stream, and then illustrating how it can predict the air emissions, the water emissions, and the amount that's removed to the sludge. A few concluding thoughts and other things that are happening here at Hydromantis, and then we'll leave a bit of time at the end for some questions and answers, and hopefully I'll have that all in and out in 30 minutes. So just for a couple of thoughts on Hydromantis, last month, I guess 2 months ago now, we celebrated our 26th anniversary as one of the leading companies in the world in producing wastewater modeling tools. We were founded by Gilles Petrie from McMaster University here in Hamilton, Ontario, Canada, and I'm speaking to you from our head office here in downtown Hamilton. And our company focuses on two things. We provide advanced engineering software tools, and most of those are based upon the concept of numerical simulation and modeling. And we also provide consulting services for wastewater engineering in both the municipal and industrial wastewater fields. So as you may know, we have 4 software products that we sell that are for the wastewater industry. Toxchem, the one that I'll be talking about today. WattPro, which is a drinking water treatment modeling package. We have GPSX, which is sort of our main flagship product that does activated sludge wastewater process simulation and optimization. And we also have CapNetWorks, which is a preliminary design tool and also does costing of wastewater treatment systems. So for today, we're going to be talking about modeling refinery wastewater treatment. And this is an area that we have been doing some work in for some time in many different ways. We know that the refinery wastewater treatment is a significant cost to refineries that are producing petrochemical products, particularly on the water side where you're looking at the cost of acquiring clean water to be able to use in the process itself. In places such as the cooling water and the opportunity to be able to clean the water that you're using within your plant, your process water for reuse, such as boiler feed water. Wastewater treatment is in and of itself an energy intensive and therefore somewhat costly process. You're supplying a lot of air to that system, for example. And the sludge that gets produced, there is a cost associated with disposing that, of course. And in the case of refineries in particular, that could be a potentially hazardous waste that has to be gotten rid of at that point. So this is a driving force to be able to optimize the wastewater treatment process. A typical large refinery could produce, up to 5 to 8 mgd of dirty process water that needs to be treated in a wastewater treatment system. And so therefore, there's an opportunity here to capture some of that water, to reuse it for process purposes. And so what we can provide is an ability for you to analyze your system, to understand where all of the components in your waste stream are going, and look for opportunities to improve that and to be able to reduce your costs. So as far as wastewater, refinery wastewater goes, the components that you could come across there include petroleum hydrocarbons, benzene, toluene, so forth, benzo, A-pyrene, chrysene, and so forth. And these all have varying levels of biodegradability, varying levels of hydrophobicity, and therefore can take different pathways through your wastewater treatment plant. There's also a number of nitrogen species, ammonia, of course, and a large number of derivative amines. And again, each of these has a wide variety of biodegradabilities under different circumstances, and some of these are available to be volatilized and some are not. So therefore, you're looking at a tool here that can help you decide how the best way to treat them. And lastly, sulfur compounds are, of course, important as well for odor purposes. And so we're going to look at an example today where we'll be modeling H2S in a wastewater treatment system. So within the refinery, the wastewater itself can come from a number of different places and therefore has a number of different potential components in them. From stream condensate systems, you can have a number of different types of neutralizing amines, cyclohexylene amine, and so forth. You can have a cooling tower blowdown that has to come through your wastewater treatment plant. It may not have a particularly large number of components or significant concentrations, but could have potentially large flows of water come to your system. Therefore, that could be challenging. Desalter blowdown can be a significant source of benzene coming to that system. And distillation column overhead and sour water stripper systems can be another source of bringing wastewater with different types of amines, filming amines in them coming to your treatment plant. And again, you have to deal with whether that's going to be biodegradable or volatilized or go out to your sludge. So Toxchem is a tool that is designed to allow you to model a wastewater treatment plant. And it's been on the market now since 1991, and it's used to predict the fate of organic compounds and metals within wastewater treatment systems. And it has been accepted by the US EPA for reporting emission rates for different types of organic chemicals. So there has been a number of instances where Toxchem is used basically to provide a reasonable estimate of something that may or may not have happened at a plant, and that can be used as a model to do an estimate, and that has been accepted by the EPA as a valid reporting mechanism. So the one thing that Toxchem does really well is this volatilization step. You can have volatilization and loss of those organic compounds in any place where you have some turbulence happening, such as these clarifier weirs, or from large open surfaces, such as this equalization basins, and then therefore obviously from aeration systems, such as this mechanical one shown here, or diffuse systems where they're designed specifically to do a lot of gas transfer. So the summary of the way that Toxchem deals with these particular systems is it looks at volatile organics for places where we can predict the mass transfer of those air emissions for the purposes of not only evaluating how much or what kind of mass transfer we have to the atmosphere, but also for worker hazards, places where there may be enclosed systems. We can model these tanks with a lid on them with a closed system, and you can get a prediction of the headspace concentration if that's relevant to predicting whether there's an explosive limit being approached. We can also model the presence of organics and metals in the actual activated sludge basin to see whether there may be interference from some sort of toxic substance. we can figure out the concentration of the components that are going to be going out with the sludge hauling, and therefore by mass balance also look at how much is left over and is going out to your receiving water. And this is important for anything that may be considered to be, an unhealthy EDC, endocrine disrupting compound, or so on. So Toxchem basically takes 4 approaches to this. We model the volatilization from open surfaces and hydraulic drops and so forth. We do the biodegradation. We have a number of different ways of doing that, and we also model the sorption. There's a couple of different sorption equations that can be used, whatever's most appropriate for each system. And oil and grease removal. So anything that is going to be, leaving the system through an API separator or a DAF is also modeled there. And then that way we can, by mass balance, figure out what remainder is leaving out through that effluent. So a visual interpretation of that is showing that you can have anything coming into the plant. We can figure out how much is removed to oil removal, how much is lost to the atmosphere, how much is being taken out to sludge, and how much is being let out to the effluent from the plant. So if you've seen Toxchem before, you may be familiar with this version. This is version 3.3. So about 2 months ago, we released a new version, version 4, which is a significant update. As you can see here, the design of this particular software is built around using these individual unit process models. So you draw out your wastewater treatment plant by putting the objects on the screen. You then specify their processes, such as the tank sizes and so forth, and specify your waste stream. And then this little table down here at the bottom provides a summary, a mass balance of the processes and the fate of each one of the components in your waste stream. So you can look at each one of these processes individually, or you can do it overall for the whole plant. This table is really quite handy, where you can click on any one of the particular components, such as acetone that's being shown here, and then immediately see that, well, 98%, in this for example, 98% of that acetone is being biodegraded in the plant. So what I'd like to do at this point is halt my slides and hop to my desktop here and show you what Toxchem looks like, and just run a really quick little demonstration for you. So like all of our software that we have here at Hydromantis, it's all based around the concept that you have individual unit processes, and you can grab and build an entire wastewater treatment plant. And I'm going to do that by putting down a DAF unit here. That first object is the incoming wastewater. And then I'm going to grab a diffused aeration tank and a secondary clarifier. So this is just a very quick, simple demonstration. So let me just zoom in on that. So you hook them together by dragging and dropping between each of these connection points. So the wastewater coming off the bottom of that DAF there, and our mixed liquor into the clarifier, and then our recycle line back to the head of the aeration basin. So if I back out a little bit, we now have to put down some effluents. And so because we're modeling all of these different pathways, we want to be able to collect up all of the different air effluents and put them into one continuous point here, which we can then specify or observe the emissions from. I'm going to grab a sludge hauling truck here, and we'll bring some solids here, and then from the secondary clarifier as well. And I will bring an oil effluent here to remove the stuff that's taken from the DAF. And lastly, the remaining effluent that goes out to the, that's supposed to look like a bank of a creek of a river with some flow going into it there. Okay, so once that's done, you can come to any one of these unit processes and then specify the depth and surface area, mixed liquor concentration, and so on. So that's done for each of these unit processes. And then the most important part is coming to the influent and specifying what your waste stream looks like. So you have influent flow, solids, grease concentration, and so on. And then you want to be able to add those contaminants. So I'm going to open up this window a little bigger here. And this is where we have our large database of the different types of components that you can add. So if I scroll down here, we have, I believe, close to 800 components in this list now. And this covers a lot of different types of things you would see in an industrial situation, refineries or otherwise. as well as a large number of microconstituents that might be present in a municipal wastewater treatment system or otherwise. We did another webinar a couple days ago on using Toxchem for microconstituent modeling. So I'm going to start out here just by grabbing a couple of simple components. Let's put some acetone in there, and let's grab some benzene. And let's add a metal here as well, just for fun. Let's put some zinc, and let's grab also some toluene. There we go. Okay, so once you've identified any number, you can make a huge laundry list here if you like of all of the different things that you want to put in your waste stream. You then specify the concentrations that are coming in for your particular plant. And I'm going to leave all these at the default value of 100 micrograms per liter just for the purposes of this demonstration so that we can sort of compare them relatively. Okay, so then once that's done, you can then just click on this button here to solve the model. And it's a steady state solution to the model, so assuming that that flow and those concentrations stay the same, we can then predict the concentration and the mass loading to each part of this plant. So for acetone, as showing here right now, these colored blocks indicate where the air emissions are going out and where they are relative to the amount that's coming in. So we have a little bar graph up here. So basically, these green blocks indicate that there's not very much acetone being released to the atmosphere at this point. And in fact, if we look at our summary table down here in the lower left-hand corner, we can see that 95% of that stuff is being biodegradable. Of course, it's a readily biodegradable substrate, so that's as expected. So if we go to something different, though, like benzene, we can see something a little more volatile. We've got some more air emissions coming off the front. This is indicating that 2.5% of our total loading is coming off at the DAF. And if we move along and look at something different, we can see a bit more loading here. So now the toluene, less biodegradable, 87% is being biodegraded, and we're losing 3% of the air. And the rest, quite a bit, is going out to the sludge here, 7.6%. So this gives you a sort of a relative feeling for different types of components that we have here. So the way that we do that modeling is through our large database of components. So as you saw when I was selecting them before, we have, I believe, close to 800 now. So if I pick one of these, for example, we can see here that the database contains, some of the information we need, the molecular weight and so forth. There is some Henry's law coefficients. I suppose I should pick something that's a little bit more volatile there. So we can see the Henry's law coefficient or Van Hoff's equations for that compound. We have sorption coefficients, a couple of different ways of describing sorption in that particular model. Biodegradation constants and half saturation coefficients for each of the components in this database. That also now includes in the new version anoxic, anaerobic, and aerobic coefficients, so we can do full DNR modeling as well. If it's relevant, there's also dissociation constants. And then lastly, we have a reference for where we got all of this data from for each one of the components that's present in our database. And lastly, I'll just quickly mention that you can generate reports here. Once you've put your model into the position where you've saved all the details and you're happy with those results, you can export directly to an Excel spreadsheet. So that this spreadsheet here with the images and all of the data shown below is exported directly from Toxchem. And you can see here these different tabs provide the details for each one of the unit processes in our model. Okay, so I'm going to close that up for a minute, and I'm going to go back to my slides again. And I will just briefly mention some of the new features in version 4. We have improved the ease of use for building the model. You may notice it's a completely new interface, some new sort of more realistic looking icons. We expanded our database. It's now about 2.5 times as big as it was before. More volatile compounds. We're now looking at including some of these EDCs, endocrine disrupting compounds, and pharmaceuticals and personal care products as well. And as noted here, this is all customizable. So if the particular compound you're looking for is not present in our database, you can take one of the compounds that's there and use that as a basis for creating your own custom compounds. And this is how some of these things can be customized for your particular plant. It is how you calibrate the model if your particular bioreactor has been acclimatized to a certain type of waste stream and you want to reflect that in the bio constants, you can do that. And this allows you to easily create new components that are relevant for your particular system. The biodegradation and volatilization has been updated in most of the unit process models. We now have full pH dependency for volatilization, and we have some more sophisticated modeling for different SRTs for the biodegradation constant to reflect a different level of active biomass in the mixed liquor of a different SRT. We've, as I mentioned, exported directly to Excel now, and we have a number of support for the sensitivity analysis tool and backsolver model tools, and I'm going to illustrate a sensitivity analysis here in my demonstration shortly. So if you have been using a Toxchem in the past and you've developed up some layouts or some custom components for your own database, they can be directly imported from the old version of Toxchem into the new version. So all of that information is available for you to use in the new version right away. So I would like to move on now to a petroleum refinery specific example at this point. Basically, I picked, along with Dave's help, some typical compounds that you may find in a refinery wastewater treatment. So for the most part, these are amines that you would see in a typical waste stream, ammonia, and then hydrogen sulfide. So this is how they're going to appear in the example that I'm going to show. So let me pop back to Toxchem, and I'll load up my demo layout here. So just to briefly describe here, this is the wastewater coming into the treatment plant. That's an API separator, a DAF unit next, and then a typical activated sludge and secondary clarifier. And then we have our associated effluent points, as I showed earlier. So if we solve the models first, and we look at some of these amines here, let me grab my, my notes here. We can notice right off the bat here that the dimethylamine is, only about 50% of that is being biodegraded in this typical plant setup. We have quite a lot of it going straight out to the effluent. Almost 30% is not being treated at all. It goes directly out in the wastewater. And there's not really any significant amount of air emissions in this particular setup of this diffuse activated sludge system. However, if we pick one of the other amines, like methylamine here, we immediately see that we are having some significant air effluents, as identified by our color scheme, 9, almost 10% here, moving out through the air. The ammonia, of course, is in a nitrifying plant, can be removed fairly efficiently through biodegradation. Nitrification in this particular case, and so for the given SRT and the given concentrations of ammonia coming into this plant, most of it's being taken up by the biology. So for example, hydrogen sulfide, again, this is a significant volatilization going on here. We're losing about 20% of that off of the DAF and the API, and of course in the activated sludge unit itself here, it's being identified in red as one of the most significant sources. You can compare the emissions from each of these different units in this table down here. In this column here, under outgoing, you can look at the specific mass emissions from each one of the units. So the API and the DAF are pretty close, pretty similar amounts, and then about 3 times that for the diffused air in terms of the H2S coming off of this particular system. And for something that's a little bit more biodegradable, cyclohexane is, well, 80% of that is being removed by this system. So for those of you who are regular users of models, there's this predictive aspect that I've shown here, and most commonly what you would like to be able to do with a model is to get a feeling of, what are the opportunities here to make some changes and to operate this plant in some way that would improve the situation. So as you may know, doing a sensitivity analysis is one of the most common and most useful ways to get a bit of an understanding of the relationships going on in this particular plant. So we have an automatic sensitivity package here that's, a sensitivity tool here that's part of this package, as it is in most of our software. And so what you can do is you can say, well, I'm going to look at one of these components. So I'm picking cyclohexylamine, and looking at its relationship to temperature. So I'm going to change my influent temperature and then run it over a range of values from, say, 5 to 35 degrees Celsius, and then see what kind of relationship I can get, an understanding of what's going on in this plant. So this green line here is showing me that that's the amount that's biodegradable, and this is percentage on this axis. So really, for the given SRT and HRT of this plant, and you know, and the concentration of cyclohexylamine that's coming in is not, it's not particularly sensitive. It's a fairly flat line, indicating that it's going to be able to do the job of getting rid of most of it through biodegradation, no matter what temperature we're moving along. But if I look at one of the other components, so if I look at methylamine, for example, and I run that same sensitivity analysis, 5 to 35 degrees, and I run that analysis, you can see in this case that there is a significant change. So this biodegradability curve, the green one, is going up with a warmer temperature, as you would expect. We can you know, move from 30-something percentage removal up to over 50 by just if we're operating at different temperatures. And as you can see, as the more is biodegraded, the green line, pardon me, the black line here is showing, of course, less and less being released to the environment. So you can do a lot of other interesting things here. We can look at how things are going to change with respect to running at different mixed liquor concentrations. So let's run different mixed liquors here from 1,500 up to 5,000, and we can get a rough feeling here for dimethylamine removal. Of course, as you have more mixed liquor and more biomass, you get more biological removal. We get quite a decrease as we go to the higher mixed liquors in the amount that's being released to the environment. So this is the water effluent here. And but of course, you are capturing more of it to the sludge as well. So this pink line is indicating an increase in the amount of that component being taken out to the sludge. And lastly, I'll illustrate for the hydrogen sulfide how that changes with pH. So if we run a number of different pH values here, let's run from 4 to 14, and I run this analysis, you can see here that the volatilization is of course dependent on the pH. So as the dissociation happens, when you move here from just below 7, or say 6.5 up to about 8, where there is a drastic drop-off in the amount of that particular component of the hydrogen sulfide that is available to be volatilized. And so therefore, as that dissociation is happening, the amount that's available to be biodegraded, because it's not leaving through the volatilization, that amount increases here. So you could potentially, if you were looking to optimize this particular wastewater treatment plant, and you were suffering and not being able to remove as much of the hydrogen sulfide as possible, Toxchem could be used to show you where you may want to move to in terms of a pH to be able to move the biodegradation up. So this is a couple of interesting things that you can do with Toxchem for refineries specifically. I'd like to sort of, this is a sort of somewhat simple example here. You can do even more sophisticated things. I'm going to load up one of our example industrial wastewater treatment plants. This one comes on the CD. If you install Toxchem, you get this layout along with it. And as an illustration, it's got 2 different process wastewaters to be treated here. A somewhat cleaner process influent water, and then an oily wastewater. And there's different components being modeled in each of these. There's chloroform and benzene and so forth. And I believe this one's got hexane in it, I believe. Yeah, hexane and dimethyl naphthalene as well. So again, we're going to leave those concentrations at their default values. But when we run this simulation and you take a look at how these different components in the waste stream compare to each other, you can see you know, immediately if you look at something like benzene, we have a lot of emissions that are immediately identified here from the activated sludge unit. This is an MBBR, moving bed bioreactor. From our equalization basin, from the cooling tower, those are places where we're getting significant release to the air. However, if you look at something like benzo-A-pyrene, this is a case where it's being mostly removed in the API and the DAF through the oil separation as well. So, and then something like naphthalene is going to be spread across many different fates in this particular case. So we're having You know, some of it being released to the air, 10%, pardon me, 8 or 9% being released via emissions in the activated sludge unit and the pond at the very end. Some going out to the sludge, and 20% almost being released to the wastewater effluent, and only about 10 of it being biodegraded. So one other feature that I'd like to highlight at the end here is our back solver feature. This is a way, instead of saying, well, I'm going to put in my influent concentration and figure out what comes out at the end, you can do it the other way around. So you can say that, well, if I want to say, I know that I have to reduce toluene coming out of that pond at the very end here down to something like 5 micrograms per liter, I can then run a scenario and to back solve and determine how much toluene can I allow into this plant. And so I know that I'm good with this particular plant setup to work up to 91 micrograms per liter. So anything less than that will keep it less than 5 micrograms per liter at the end. So it's kind of a way of using a back solving tool to figure out what's the allowable headworks concentration that will keep me within my acceptable range downstream. And this becomes more interesting as you've got more complex things happening at a plant like this one with some recycles and with a couple of different influents. Okay, so I'm going to hop back to my slides for a few concluding thoughts here. As I mentioned before, we know that Toxchem can be used to report emissions for Clean Air Act amendments and SARA reporting. We know a number of people use it for designing and optimization of process schemes to, reduce air emission, whether I could move to a different pH, if I could recycle something different or operate at a different SRT. We know for people who do it for studying how much is going to be going out to the sludge, to estimate maximum allowable headworks concentrations for places where there's sealed or capped systems that have headspace concentration issues. And basically, I think one of the most common uses is just looking at what is the inventory and mass balance of all of those components as I go through the plant. Just being able to sit down and sort of evaluate what the model is telling me is often a very useful and insightful process. So just to wind up, I like to summarize how Toxchem works. It's 3 simple steps. You build your plant, you select your contaminants, and you load up your system, and then you observe what those emissions are going to be. And then you have lots of opportunities to do sensitivity analysis, to run a number of different scenarios, and get a lot of interesting information out. So one last comment here quickly about GPSX. So I know some of you are GPSX users as well, and so one of the questions is, can you model refinery wastewater with GPSX? And so the answer to that question is yes, with some help from us. We have the ability to combine the models from Toxchem into GPSX to do dynamic modeling. And we do have a special in-house activated sludge model called Mantis IW that is specifically for industrial wastewater. So it's not part of regular GPSX, but we can be hired to do some modeling on your behalf using that. And just to highlight the differences between what you would normally find in an activated sludge model, here we can see that in Mantis IW we have broken out the number of different types of substrates and the different types of COD into all of these typical types of industrial components that you may know something about at your plant in terms of their loading into the wastewater system, and so we can model that with a bit more sophistication. So I'll mention a few quick things at the end here. For those who have been using our video library on our website, we have now added a new section for Toxchem, so you can go up to the video tab on our website and check out our new Toxchem videos. They include all of our tutorials and illustrate how to use Toxchem. We are continuing our educational webcast, just like this one today. We're going to be talking about capped works in a couple of weeks, and then in early August looking at how to design and optimize upflow anaerobic sludge blanket reactors using GPSX. We are continuing to offer web-based training for all of our software. You can find out more about that on the training tab at our website. And I'll also mention briefly that we do offer quite a lot of services that go along with our software, doing modeling consulting, building and calibrating models for you, designing sampling programs to help you calibrate your models. And basically, we can be your go-to people for doing our modeling. We are the modeling experts, and we often like to work with our clients to come in on bids and be their modeling people as part of any bid that you may be doing on a particular project. So if you're interested in teaming with us, please give us a call and we'd be happy to help you out. So if you ever have any questions about Toxchem or any of our other software, you can always contact me, Spencer Snowling. I'm at my last name, Snowling, at hydromantis-software.com.